Okay, good afternoon all. Today our class is about predicted logic. So today we should have quantification, universal, existential, domain of quantifiers, negation, nested quantifiers. So let's just start. What mean by quantification? Quantification is to create a proposition from propositional function. So here we need to create a proposition from propositional function. As example, in English, the words all, some, many, none, few are used in quantification. So here we will, if we have these words, how I can apply it in mathematics or in a propositional. We focus in two types, quantification as universal and existential quantification. So let's go. We will start with universal. Universal mean all. So in example, the the definition is universal quantifier. Let B be a predict with domain of disclosure D. The statement for every x, bx is said to be universal quantified statement. So here for all x, bx will be. So here the symbol, this one, we have it for universal, mean for every. So if I need to read it for every x, bx can be written as for the universal or for every x we have px. So all the domain should be correct with bx. Universal can be read as for all, for every, for each. Both of three of them is correct. If I say for all, for every, or for each, that means any x in any x in the domain can get bx. It's correct. Okay, example. Let bx be the statement x plus 1 greater than x for all real number x. That means he needed from me to prove is for each x bx true. According to the definition, the all x on this domain should be correct, true. So we need to prove is this correct or no. So I mean any number I put it in here for x should give me correct statement. So for bx is true for all real number x. This is what I need to say. For bx as a function is true for all real number x. So the quantification for each x bx is true. That means I approve it at least for one. That means for all is correct. This is the universal or for each. Okay, let qx as a function be the statement x smaller than 2 where the domain consists all of real number. So I need to go to all real number x, the domain is all real number. So I need to see for each x qx is true or no. The quantification for x qx is false since it is not true if x is real number 2 or greater. So here as example, if I said x is 5, so the equation is not correct. That means the condition is not correct, so it's false. Let's go here, return to previous slide. If let's say if x be 2, so 2 let's say that x equal 2, so x plus 1 equal 3. So according to the equation is greater than 2, bigger than 2, so it's correct. If we return here, he told me any real number x is smaller than 2. So let's go here. Let's example x equal 1 is correct. 1 smaller than 2 until now correct. But if I say 3, x equal 3, so here is less than 2, false. So we cannot have, so the equation here or the function here is false, because at least I have one element or one number is not 2 for it. So I cannot say for all element or for all real number qx is correct. It's false, because at least I find one number is not correct. Okay, we can assert a universal quantification is false by providing a counterexample. So we can prove it by using counterexample. So counterexample for each x bx, an element for which bx is false. So if I find one false, that means is not correct. We can use counterexample to disprove a universal quantification as a true, not to prove. So it's like counterexample. I will find bx false, so I can disprove the universal quantification. If the domain of disclosure is all real number, is the for each x we have x power 2 greater than x, true or false. So here false, because if x equal half, so x2 x power 2 will be quarter is bigger than half? No. So at least I have one element is not correct, the proposition for it, so I cannot say for all element it's true. At least I find one false, so it's not correct, it's false. Okay, the previous one was universal for each element. Here no, we will have one existential quantifier. At least I have one, not all elements. If I want find exist x, so here let be a predicted with domain of disclosure D. The statement here we have there exists x for bx, so I have one element for bx, we call it exist. I find already this element, we call it exist, is said to be an existential quantified statement. So we can have it, we can write it like this: this means there exists x, bx can be written in this way. So this means there exists x for bx. We can say there exists for some, or there is. For example, let qx be statement x smaller than 2 and x is a real number. So here he need to see if it's correct or false. So we have x smaller than 2. For quantify for all, if I need to check for all universal or for each x, qx is false because at least I have 1. So if I say if x equal 4, the statement will be false. But at least I have 1. So let's say that x equal 1.9. Okay, because he said real number, 1.9 is a real number. So 1.9 a real number, we can say x smaller than 2, so it's correct. So for here there exists x, q, x, correct, true. Since I find x equal 1.9, so at least less than 2, so it's true. For each x, q, x is wrong. For x there exists x, q, x is correct, true. Okay, let's have another example. Let Bx be in statement x plus 1 equal x. For all real number, I need to check there exists x, Bx true. Let's see. Because Bx is false for every real number, so Bx is false for exists there Bx. So I cannot find this element, because if I need to prove it, let's have x equal 1. So 1 plus 1 equal 2 cannot be 1. Sorry, 1 plus 1 equal 2 is not equal x, not equal 1. So for Bx, for every real number is false. So I cannot say there exists Bx true. So the statement is false. Okay, let's have another. Let Rx be the statement x divide 2 equal x. For a real number, is there exists Rx true? Need to prove. Rx seems like false for any real number, but since we have 0 divide 2 equals 0, so it's true. Let's try. He told me x divide 2. Let's have 2 divide 2 is 1. 4 divide 2 equal 2. So for it's look like for all real number is false, but since we have 0 divide 2 equals 0, so there exists one element is true. So this proposition is correct. Okay, let's go for the domain. Domain of quantifiers can be expressed in mathematical form. Given x is real number for 1 and 2 and integer for 3. So for each x belong to R, Bx. For each x belong to R, we have x plus 1 greater than x. There exists x belong to z, x divide 2 equal x. Note that true if x equals 0, just according to previously. So let's go for precedence of quantifiers. Precedence of each element or each x or there exists is higher than not and or. So if I find it, it's higher than and or not. So it's the first step I will do it if I find for each universal or there exist. So here for each x bx or qx. So here sorry, for exist for each x bx and qx. So I have and here, or I have also for each. According to the rule, for each is higher than and, so I will start for each. So I will go here for each x bx, then the result will have it with the qx. Clear? So I put the precedence here to clarify that for each x is higher than and. We cannot say like this because it's not for both of them, it's only for p. See, it's only for p. Here the equation for each is only for p, not for p and q. So this way is wrong, it's not correct way. If x like black, pink, then he like cable. Is this a quantified statement? For all people, it holds that if the person like black, pink, then she like